Assalamu alaikum dear student. My name is Dr. Muhammad Aznan Asghar and today we are going to discuss the covalent bond and maybe the metallic bond in this lecture which is under the bonding in solids. So far we have discussed about the covalent bonding in detail, like single covalent bond, double covalent bond, triple covalent bond, expansion of octet and some advancement including the particle wave nature and duality, uh, atomic orbitals, wave functions and nodes, and discuss the different orbital overlaps, symmetry and molecular orbitals. As we already discussed the bonding and anti-bonding molecular orbitals and the overlap of 2p orbitals to give the sigma p bonding orbitals, anti-bonding and pi bonding and anti-bonding orbitals. So for molecule in which both s and p outer shell atomic orbitals are involved in bonding, the schematic energy diagram I would like to show of this type of compound is here. The actually sigma s and sigma star s orbitals are of lowest energy and would be occupied first by electrons. Next come to sigma p and pi p bonding orbitals, followed by their respective anti-bonding orbitals. The pi orbitals are actually doubly degenerate since the two sets of orbitals formed by the interaction of px and py atomic orbitals have same energies. To evaluate the bond order, the combined total of available valence electrons in s and p orbitals on the two atoms that form the molecular orbitals are actually fed into the molecular orbitals two at a time, starting from the sigma s orbitals. For example, in case of fluorine F2, we can see in this picture, which has a smallest electronic configuration. We know that 1s2, 2s2 and 2p5. There are 14 valence shell electrons available, and these occupy molecular orbitals as shown in this figure A. This is actually the A I would like to show. The highest occupied molecular orbitals are pi star p molecular orbitals, leaving the pi star p molecular orbital empty. The net effect is that the fluorine F2 molecule is held together by single covalent bond with a pair of electrons in sigma p orbital. The energy level diagram for oxygen is shown in B. This diagram we can show. But there are two electrons less occupy the molecular orbitals. We know that the following Hund's rule of maximum multiplicity, the highest occupied molecular orbital HOMO are actually the two pi star p molecular orbitals which have only one electron each. Consequence of this are at first the oxygen molecule has a bond order of 2 and is said to be the double bonded, and second, oxygen is paramagnetic due to the presence of unpaired electrons in pi star p orbitals. The resulting bond orders have a direct effect on the bond strength and bond length. Thus, the bond energy for doubly bonded oxygen is actually 493 kilojoule per mole with a bond length of 1.2 angstrom, whereas singly bonded fluorine has a bond energy of 155 kilojoule per mole and the bond length which would be equal to 1.412 angstrom. For the energy level diagram shown in this picture, there is no interaction between s and p orbitals. In many cases, the interaction between s and p orbitals does occur. However, as shown by detailed calculations of orbital energies, which give the sequence of molecular orbitals on the energy scale and by various electronic properties. The idea of orbital mixing also forms the basis of hybridization, which we have discussed already in detail in our previous classes. The interaction of sigma s and sigma p molecular orbitals and their resulting energies is shown in this schematic diagram. It is no longer appropriate to refer the new orbitals as bonding and anti-bonding, and they are therefore labeled as simply sigma 1 and sigma 2. Similarly, sigma p star and sigma s star molecular orbitals can mix to give two new hybrid orbitals, sigma 3 and sigma 4, as shown in this figure B. Pi molecular orbitals are not involved in such kind of interactions, mixing interactions. The resulting energy level is which is appropriate for the molecules, for example, of nitrogen, is shown in this diagram. The sequence of energy level is now different to that is shown previously for our fluorine and oxygen atom. The difference shown is that the sigma 3 orbital has higher energy than the pi p orbitals. This does not affect the bond order of nitrogen N2, which is 3. It means there is triple bond between the N2 molecule. The bond energy of nitrogen is 942 kilojoule per mole, and the bond length is 109 angstrom. We may next consider the diatomic molecules in which the two atoms are not same. Consequently, the energies of their individual atomic orbitals are different. So, orbital mixing of resulting molecular orbitals occurs to various extents, and resulting energy level diagrams are often symmetric. In addition, if the two atoms have significantly different electronegativities, bonding is a mixture of covalent and ionic. A good example of polar covalent bonds in the HF molecule, for which the energy level based on molecular orbital theory, and we already discussed this. This illustrates a number of features and which are important in bonding of solids, and such as oxide, and I would like to show the different others. This is actually the example of HF molecular orbital diagram. The energies of the participating atomic orbitals depend very much on the position of the periodic table, and in particular how much the electrons in these atomic orbitals are shielded from the nuclear charge. The hydrogen 1s electron experiences unit positive charge from hydrogen nucleus and is of higher energy than 2s and 2p electrons of fluorine, so which are not well shielded by the inner 1s electron from the nuclear charge of 9 positive. The 2p orbitals are partially shielded from this nucleus charge by 2s electrons, whose orbital penetrate more deeply towards the nucleus, and hence 2p electrons have higher energy than 2s electrons. Fluorine is a much more electronegative element than hydrogen, and so the bonding electrons are strongly attracted towards fluorine, giving a net negative charge, partial negative on fluorine, and an associative positive partial positive charge on hydrogen. The 2s electron on fluorine F do not take any effective part in molecular orbital formation, since they are rather tightly held to the F nucleus and hence remains in an individual atomic orbital of same energy in the molecular orbital diagram as shown in this figure. These may therefore be regarded as occupying a non-bonding orbital. The pi bonding orbital formed by overlap of H1s and fluorine 2pz orbital is of lower energy than the contributing atomic orbitals, but it is closer in energy to that of fluorine 2pz orbital. We can see in this picture quite clearly. We may say that this is the sigma orbital retains strong pi characteristics of fluorine. Conversely, the sigma star orbitals have rather similar energy to the contributing hydrogen 1s atomic orbitals and therefore retains strong s characteristics. The 2px and 2py atomic orbitals on fluorine do not interact with the H hydrogen 1s orbital and therefore remains as non-bonding orbital in energy level sequence. Molecular orbital theory has been very successful in accounting for bonding, spectroscopic and sometimes the magnetic properties of molecules, as well as we shall see later that can be extended to crystalline solids and in modified form to metallic bonding. We would like to approach the next valence band theory, which has many attractive features, not least its simplicity in relating bonding to coordination geometry and oxidation states. Now let's talk about the valence band theory, which explains the electron pair repulsion, hybridization and the oxidation states. The valence band theory, next I already discussed that the valence band theory has many attractive features, not least its simplicity in relating bonding to the coordination geometries and oxidation states as well. The valence band approach or covalent bonding focuses on the outer valence shell electrons of atom. Basically, they can do one of the four things that I would like to mention here. The number one is they form electron pair single covalent bonds by sharing of one electron each from the two atoms that form the bonds. Number two is the two electrons from same atom occupy an atomic orbitals. They form a lone pair in a lobe-shaped non-spherical orbital. This lone pair generally occupies a region of space. Instead of bonding pair, the lone pair is described as stereochemically active. The third one is two electrons from the same atom may act to form a single covalent bond between two atoms, such as bond is called a dative bond. The fourth one is pair of electrons, one from each atom may take part in multiple bond formation to add the single bond between the same pair of atoms. Double bonds, triple bond and occasionally even quadruple bonds are formed in this way. So coordination numbers and geometries around the central atom are given by the combined total of covalent bonding pairs and lone pairs of electrons, working on the principle that electron-electron repulsion actually causes these pairs of electrons to arrange themselves in a such a way that to be as far apart as possible in space. The ideal shapes with some examples are for the coordination number ranging from 2 to 6 are given in this table. This is actually the coordination number and geometries of different molecules possessing different shapes as well as number of electron pairs. The ideal shapes, however, the lone pairs are held more tightly to a nucleus than the bonding pairs, which effectively means that they occupy more space and cause distortion from ideal geometries and symmetries as well. The strength of electron pair repulsion is actually the in following sequence. Lone pair repulsion is quite stronger than lone pair bond pair repulsion, and the very least one is actually the bond pair and bond pair repulsion. Two familiar example of distorted shapes of small molecules which are NH3 and H2O is shown in this figure. Here we can see that NH3 has one lone pair on nitrogen atom and three nitrogen and hydrogen covalent bonding pairs, but the lone pair exerts a greater influence on the shape, and while the H and H bonds, which are actually the covalent bond between the nitrogen and hydrogen, bond angles are reduced from the ideal values of 109.5 to actually 107. In water, again the hydrogen oxygen hydrogen bond angle is reduced from ideal bond angle, which was 109.5 degree to 104.5. The above section actually gives a brief summary of the valence shell electron pair repulsion theory, which is widely used to account for the shapes of molecule. Multiple bonds do not have a major influence on shapes, since their geometry's disposition is essentially the same as that of single bond. Nevertheless, since they contain more than 2 electrons, 4 for double bond and 6 for triple bond, they do not exert actually a greater repulsion on adjacent electron pairs. From our knowledge that we discussed in different both the Vesper theory, knowledge of shapes and disposition of atomic orbitals on particular atoms, it quickly becomes apparent that modification of some of the atomic orbital is required to account for Vesper geometries. For example, methane, methane, a CH4 molecule, the three 2p atomic orbitals are and the 2s atomic orbitals on carbon are not expected to be arranged specially in the form of tetrahedron, because of the 2p atomic orbitals are at right angle to each other and 2s atomic orbital is spherically symmetrical. So to account for the changes in orbital structure and are required to permit the formation of 4 equal carbon hydrogen bonds in CH4 methane and many other similar cases, the concept of hybridization was introduced. In hybridization, S and P and sometime and D atomic orbitals and combined to give an equal number of hybrid atomic orbitals, which are then able to overlap with atomic orbitals on adjacent atoms, leading to the covalent bond formation. And we are very much familiar about the terms hybridization, and we have discussed the we have already know the wide concept of hybridization behind different molecules to explain the different properties and different effects of molecules in terms of hybridization, in terms of atomic orbitals and the hybrid atomic orbitals. The distribution of lobe-shaped hybrid orbitals that are postulated to form uh, on hybridization of different members of sp and d atomic orbitals are summarized in this table. We can see that the shapes are the same as those given in the previous table, but the two lobe tables are actually the self consistent sense, since the number of occupied hybrid orbitals governs the coordination geometry. Here we can see that if one s and one p atomic orbitals combine, they will form the two sp hybrid orbitals which have same energy and shape as well. So the sp hybridization would yield the linear geometry, and sp2 may yield the triangular, while the sp3 is tetrahedral, while sp3d orbital would yield the trigonal bipyramidal, while in the case of sp3d2 the shape would be the octahedral, and sp3d3 pentagonal bipyramidal would be the shape of that molecule that possesses the hybridization sp3d3. To complete the process of assigning electrons to either bonding pairs or lone pairs, knowledge of periodic table and elemental ground states, as well as the possible excited state along with the usual oxidation state adopted by the elements in compound formation, is actually required. To describe the electronic ground states of elements, the simplified scheme used is actually the only those electrons that form a part of outer valence shell are specified. The inner core electrons are simply lumped together in configuration expected for the appropriate noble gas element. For example, the first row p block elements may be represented as helium. If we talk about the if we include the electrons of helium, then where n is equal to 1, then the boron for 1, 2 for carbon, 3 for nitrogen, 4 for oxygen, 5 for fluorine. The first row transition series may be represented as 4s2 3dn. N may be 1 for scandium, 2 for titanium, etc. We would know that. 6 for iron, 7 for nickel, and 10 for zinc, 9 for copper. An old-fashioned but simple pictorial and very useful way to represent the valence shell electrons is actually by their occupancy of a series of boxes, with one box for each atomic orbital, as summarized in this picture. Some example I would like to show. Of course, the electrons do not occupy the boxes, but this scheme does allow us to actually distinguish between lone pairs and the unpaired electrons, and between the ground state and the excited state. And it would also provide the information to identify which empty orbitals could be occupied by acceptance of electron pair donated from an adjacent atom to form a dative bond. For example, in example 1, the carbon has two unpaired electrons in 2p orbitals, and it would actually therefore a divalent unless the uh, electrons in 2s orbital could be used in bond formation. To obtain the normal tetravalent state of carbon, one of the 2s electron is regarded as being promoted to the empty 2p orbital, giving 4 orbitals each with a single electron. Following hybridization of these 4 orbitals to give 4 equal sp3 hybrid orbitals arranged tetrahedrally, carbon is able to form the 4 electron pair covalent bond by accepting an electron into the each of sp3 hybrid orbitals from surrounding atoms, as in CH4. We can see this is actually for the CH4. In example 2, example 2 is actually a phosphorus which is in ground state would be a trivalent since it has 3 half occupied 3b orbitals. Many trivalent phosphorus compounds are known, which are held together by 3 electron pair covalent bonds. The shape of these molecules are usually pyramidal rather than planar. However, since the lone pair of electrons originating from the 3s orbitals occupies a stereochemically active sp3 hybrid orbital as a consequence of hybridization, the resulting bonding pair and lone pair repulsion give rise to the pyramidal shape. This is actually the reason behind this pyramidal shape. An additional feature of compound formation by phosphorus is that orbital expansion can occur, which we have discussed already, in which the one of the s electron is promoted to the empty 3d orbital, giving rise to a half-filled orbitals. This allows actually phosphorus to exhibit either the group valence of 5 by forming 5 electron pairs covalent bonds, or valence of 3 that is 2 less than the group valence. An additional complication with the phosphorus is that the second 3d orbital is potentially able to accept an electron from a negatively charged ligands such as F negative fluoride, forming an octahedral complex such as PF6 negative, in which sp3d2 hybridization scheme gives 6 equal hybrid orbitals and an octahedral shape. Example 3 is of beryllium, for which one of the 2s electron is promoted to an empty 2p orbital to giving the valence state of the 2, but the 2 empty 2p orbitals are able to accept electron pairs from the negatively charged donors, giving actually the sp3 tetrahedral coordination. The bonding in crystalline BeF2, which is isostructural with silicon dioxide and has a three-dimensional framework structure formed from the corner sharing PeF4 tetrahedra, which may be rationalized using this valence band scheme. Thus, each fluorine atom forms a single covalent bond by the sharing one electron with the beryllium atom and a dative bond by the donating an electron pair to the empty sp3 hybrid orbital on a second beryllium atom. Hence, fluorine is a 2-coordinate, but BeF-Be linkage is non-linear because fluorine has 2 lone pairs in addition to the 2 bonding pairs. Example 4 is actually the silicon dioxide with a similar structure of BeF2 I already discussed, but in this case silicon is actually in excited state, has 4 half occupied sp3 orbitals, each of which shares an electron with surrounding oxygen, and each oxygen has 2 half occupied orbitals for covalent bond formation with silicon. But again, silicon oxygen silicon bond is non-linear because of the 2 lone pairs on each oxygen atom. So it is interesting that hybridization concept, which forms the basis of valence band theory, has many similarities to the ideas of orbital mixing, that is a key point of molecular orbital theory. Valence band theory is attractive since it allows us to rationalize and predict coordination geometries, including the presence of stereochemically active lone pairs. It includes dative bond formation in which both electrons in a covalent bond are provided by more electronegative atom. It also relates the number of lone pairs and bonding electron pairs directly to the element oxidation state. However, Bell's band theory does not, however, have anything to say about the spectroscopic properties associated with the electronic transitions between the energy levels or magnetic properties which was associated with the unpaired electrons unpaired electrons, and for which molecular orbit is much more useful. In addition, the ideas of molecular orbital theory as applied to small molecules can be readily extended to the bonding in these crystal structures which exhibit metallic bonding, and which will be discussed in next lectures. Thank you very much.